Okay, so welcome everyone. Welcome to Flower Monthly for February. My name is Nick, and I'm joined here by Daniel, and we have got a jam-packed Flower Monthly session for you. Let me just outline our agenda. Um, we've got a few flower updates we want to share, some really exciting news that I'm sure many of you will be sort of really interested to hear. And after we've shared this news, we're going to jump into two invited talks. We've got our first invited talk by Royson Lee, who works for Samsung AI as well as studies at the University of Cambridge. He's going to be telling us about a paper that appeared at NeurIPS 2023 that looks at federated learning and how it can be suitable for personalization, but from a meta learning perspective. So it'll be a really exciting technical piece. And then we'll be closing Flower Monthly with another really interesting piece of work. It's motivated by the very sort of hot off the press EU AI Act, which is likely to be first of many steps towards regulation of various kinds. And so we've been thinking with TU Munich and IBM at Flower as to what are the changes that this would mean for the priorities for federated learning. And so we've got Herbert Heuschlager here to tell us about that. So before we get to those two talks, let's give a couple of updates for the month. The first of these two updates we want to give is related to the Flower AI Summit. This is fast approaching. It's a hybrid event, but the physical instantiation of it will be in London. It's going to take place on Thursday, March the 14th, and Friday, March the 15th. And in keeping with how we ran the event last year, it's going to have 2 days. The first day, we're going to do a focus on the innovations and the progress that's been made in the world of federated learning and related techniques over the last 12 months. I will be looking at things such as the Flower roadmap for the preceding time ahead. We've got some incredible invited speakers, and the real focus is on the science of federated learning and how it's rapidly maturing to the point that it can be adopted. And so then naturally, the second day speaks about adoption. And so we have some fantastic companies, organizations, NGOs, representatives of many organizations that are using technology of this kind. You can see interesting progress in things like pets, places like finance, domains like healthcare, and so on. And so day two will be really dedicated to looking at these successful deployments, understanding how practices are evolving, and advances in things like standardization. And so we have, if you're thinking about attending physically, we have a wonderful venue for you. It's about literally 3 minutes walk from King's Cross. I was there a couple of weeks ago. It's a really beautiful venue, but there is a maximum capacity. And so if you want to attend in person, I really strongly suggest that you register today and secure your place. In between the 2 days, we're going to have a really nice social event across the road where you can network and really dive into some deep discussions with folks in the domain. There are also slots for posters and demos. So if you're doing work in the space and you want to participate even more intensely, feel free to go to the URL that you see at the bottom here, register not only to attend, but register to present your work, your deployment, your proof of concept in this area. The thing I really want to kind of highlight in this session was our first batch of speakers. And so, as I mentioned before, we have in day one, the AI Research Day on March the 14th. And so the types of topics that you'll hear discussed during this day includes so the roadmap for the flower ecosystem, technical advances and how you can do things like decentralized learning. We'll be touching upon how LLMs can be used to be trained using sensitive data. And by the way, these are the topics that many of our speakers are going to be touching upon. So both Flower Labs, parts of the team, as well as invited speakers. We'll also be talking about how you can accelerate just basic science using federated learning, or how we're starting to enable things like FedOps to be more scalable and easier to do. The types of speakers that we've got are coming and speaking include Virginia Smith, one of the pioneers in the world of federated learning. We're going to have talks by faculty at places like UNC Charlotte or UMass Amherst. For example, Duke has a really great new uh, location out in China, and those folks have built a system called Fed Campus, where they're actually using privacy preserving techniques to help monitor and automate and make the campus smart. And so we have a variety of speakers of this kind talking on day one. I'd also highlight Andrew Sultan. He's a researcher, but also a medical professional, and he managed to deploy Flower in a number of NHS sites and actually use Flower to process 130,000 patient records during the years that spanned COVID. So this is the kind of speakers that you'll be hearing from during the AI Research Day. And then the next day, we're going to have AI Industry Day. And so we'll be hearing from a different kind of variety of speakers. These speakers are working in various organizations that need the type of advances that federated learning can provide. And so we're lucky to have people like Tim Hospitalis, who's the head of Samsung AI in Cambridge, speaking about how Samsung is using Flower to prototype new types of federated learning. We have a wonderful speaker, Sherry Ding from AWS, who'll be talking about how you can combine the power of AWS and Flower to stand up important types of federated learning systems. And so we have a variety of folks who are going to be talking about deployments, practices, new data sets. For example, Mina, who works for Zinzak, which is a subsidiary of Volvo, is talking about a new data set for doing self-driving cars that can be federated, and she's been using that to understand the domain in more depth. We also have a fantastic speaker from Zama. Zama is an open source specialist in the world of homomorphic encryption. And so Roman is going to be talking about how Zama and Flower can work extremely well together in the situations where your deployment really needs the highest levels of security. And so that's the kind of flavor of talks you'll get from the Flower AI Summit this year on day two. Go to our website to see the more details about all the various speakers we've announced. You'll also see there some of the early releases of posters and demos that they're also going to be part of the show. So we hope to see many of you there, and yeah, we're really looking forward to it. I'm now going to hand over to Daniel, who's going to speak about our next sort of major announcement for the month.
Thank you so much, Nick. The big announcement, as some of you might have already seen, is Flower 1.7. We released Flower 1.7 on Monday, and you can update by running pip install minus uppercase U FLWR. And I can highly recommend everyone who is using Flower update to the latest version, because it comes jam-packed with a huge number of improvements. And it also sets the stage for some major developments that we'll announce pretty soon. Next slide. Flower 1.7 is a huge release, actually, and it also shows that our development pipeline is accelerating. Flower 1.7 comes around about 2 months after Flower 1.6. And in this short amount of time, and keep in mind, we had the holidays and New Year's and so on, we merged 169 PRs. So there's big changes under the hood that happened in Flower 1.7. Next slide. Some of the highlights are on this slide. I want to start by actually I want to start with the bottom row because I'm personally quite excited by that. We have a number of new code examples, and all of the code examples you see on this slide were contributed by the community. That's why I want to give a big shout out to the contributors who created these code examples. All super useful things that we haven't covered in our documentation or code examples that well before. So there's one code example that shows how to use Flower via Docker Compose. In our regular code examples, you sometimes see that you have to open multiple terminals and install dependencies and so on. And in this code example, pretty much all of this gets automated away using Docker Compose. So I can encourage everyone to check it out. There's also a code example on sklearn with tabular data, something that's very important in many industries. And then another code example that shows how to aggregate custom metrics on the server side. This is something that's also in the current tutorials, could be covered maybe a little bit better, but this code example goes into all the details and shows a fully fledged example that you can just adopt to your own use cases. Let me go into features that Flower 1.7 brings. Probably one of the biggest features is support for stateful clients across both virtual clients and networked clients. We always had the possibility to create instance variables in the case of networked clients. So if you use start client or start numpy client and you have your client class and you create instance variables, you were always able to have this a stateful client that keeps its state across multiple rounds of federated learning. But this wasn't really possible in the case of simulation. So if you use the simulation engine, if you use virtual clients, then all of that state was gone because the clients are just temporarily created when they're needed. After that, they're destroyed again by the virtual client engine to make simulations as scalable as possible. So there's good reason for destroying clients, but the issue for many was that if you want to run some more advanced protocols that need state on the client side, this wasn't really possible without any major hacks. It was possible, but not in a super nice way. Now with stateful client support, you can run the exact same client across both virtual simulated settings and also networked settings without any code changes. And it's a major feature that will enable much more advanced client-side training schemes in a simulated environment. We have official support for Python 3.11. We've had it for a while, but now all of the CI checks, everything is running on 3.11, so you can absolutely bet on 3.11 working. And then we have a number of other features that I will now discuss on separate slides. Can we go to the next one? The first one I want to highlight is XGBoost support for cyclic training. Since we launched XGBoost support, it was actually a very warm welcome from the community. This is something that is in high demand, we see. And with Flower 1.7, we're releasing one new strategy that's called FedXGB Cyclic. And it's really remarkable. It's quite different from all the strategies, pretty much all the strategies actually that we have so far, not just XGBoost, but also the other ones. Because what it does is it performs cyclic training. And what this means is the server sends the model to one client, that client trains the model for a little while, sends the model back to the server, and then the server sends it to the next client. So we do a client-by-client training without modifying it on the server side. And this is quite different from the typical federated approach where we send out the model to multiple clients and then we receive back results and we aggregate them. In this case, we just basically hand the model over from one client to the next one, always going through the server, of course. And you can check out the strategy, how it's done in FedXGB Cyclic. And there's also a very comprehensive code example called XGBoost Comprehensive that covers all the details and shows you one end-to-end working example. If you're interested in doing something similar for something that is not XGBoost based, feel free to check out the strategy, how it's implemented, and I'm pretty sure that it can be adapted to different settings in quite an easy way. Next slide, please. Another feature is Apple MLX support. So Apple released a new machine learning framework, something that was quite surprising to many of us. And literally a few days later, I think 2 days or so, we already had it integrated with Flower. We have a new quick start example, quick start minus MLX. And it shows how you can use this framework on a Mac environment to do federated learning with Flower and Apple MLX. Next slide, please. A big feature request that we had for a while, and we had preliminary support for that, was better Docker support. And with Flower 1.7, we finally have a big documentation page that outlines how to use Flower and Docker. And we are also launching official Flower Docker images. Flower 1.7 comes with an official Docker image for the Flower server. And then in the next release, we'll also support an official Docker image for the Flower client. So Docker support is here, and it's only going to improve with the upcoming releases. Next slide, please. There's also one deprecation. It's quite a big step, something we had for a long while. Everyone who's followed one of the quick start tutorials has probably seen our beloved NumPy client. NumPy client is obviously still supported and still around, but the way NumPy client is started is right now in Flower 1.7 is by using a function called start NumPy client. So you create your instance of a subclass of NumPy client, and then you pass it to start NumPy client. Starting with Flower 1.7, that is actually deprecated. Next slide, please. And we are converging start NumPy client and start client together, and going forward, all the clients should just use start client. So this is something where we, again, unify our API landscape a little bit, and we make it easier going forward because there's just a single function that you need to know in order to start a client. If you're subclassing NumPy client, then obviously this is not an instance of Flower client.client, but it's an instance of Flower client.numpy client. So in order to make it compatible with start client, you need to call a new convenience function that has been around since Flower 1.6 that is simply called toClient. So it's pretty much the same as before. You create your instance, and then the only small difference is you call .toClient, and then you pass this new instance to start client as always. That's a big change. I can encourage everyone to immediately migrate to the new behavior. If you continue to use start NumPy client, you will see a deprecation warning in your logs. So the new behavior using start client is the recommended way of doing this going forward. Next slide, please. And then last but definitely not least, Flower 1.7 is a lot more memory efficient. It's the most memory efficient release that we've had so far. In one of our benchmarks where we ran federated averaging with 100 clients training a vision transformer, we saw a decrease in memory peak of 39%. So Flower strategies are getting way more efficient because we now switch to in-place aggregation. That's something, it's enabled by default. So once you upgrade to Flower 1.7, you should automatically see those gains. And I think it's especially interesting for resource-constrained environments. For example, if you were to run the Flower server on a Raspberry Pi or similar device, I think this will be a very welcome improvement. You can disable it. There's a flag on each strategy that uses it, and you can just disable the in-place fed averaging to get the previous behavior. But there's really not a big reason to do this. And by default, it will use a new behavior, and you will get much more memory efficient aggregation. Next slide, please. Another big update is Flower baselines. We updated and created new baselines. So there's overall 6 baselines that have changed or that have been added since the last release. You can see a screenshot here from the Flower baselines docs. And you can see that we now have a really a substantial list of baselines that you can just go ahead, use, customize for your own research or prototyping purposes. If it's been a while since you last checked out Flower baselines, then I can highly recommend checking it out again. There's now, the list has grown substantially, and individual baselines have been updated and much improved. In no small part, thanks to big efforts from Javier, and also all the contributors from some of reproducibility. And we'll give a bigger update about Flower baselines during the Flower AI Summit 2024 in March. Next slide, please. So again, I can highly encourage everyone to just pip install update to the latest Flower release 1.7. There's also, apart from the things that I've shown, there's many more things. Feel free to check out the full release notes. And one of the things that I also want to highlight is that we made a ton of under the hood changes that make Flower 1.7 really future-proof for important developments that we yet have to announce. Next slide, please. So that's Flower 1.7. It's available since Monday, and you can update right now. Flower 1.8 will follow in February already. So what you can see here is that we accelerate our release schedule. Previously, the releases were a little bit further apart and were quite big. And what we're doing now is we want to get changes that we make as quickly as possible into a stable release and into the hands of the entire Flower community. Flower 1.9 will follow in March already. And then after Flower 1.9, there's obviously a big question, what should we call the next release? But the one thing we know is that the release after Flower 1.9 will follow in April. So there will roughly be a release every 4 weeks. If you're curious to see and understand what will happen in Flower 1.9 and beyond, join the Flower AI Summit 2024 to learn more. And you can register now on flower.dev. And that concludes the update about Flower 1.7.
Wonderful, wonderful stuff, Daniel. Thanks so much for sharing. I'm sure everyone is rushing off to try Flower 1.7 as we speak. But I would say before you rush off to try it, you should listen to the next 2 talks. So we've got 2 great talks coming up. We're going to start our first talk now. This external invited speaker is Royson Lee. As I mentioned earlier, he works for Samsung AI and he studies at the University of Cambridge. And he is going to speak to us about a technique that's actually embedded inside this paper called Fed-L2P. And so I will hand over to Royson to give his talk.
Okay, thanks, Flower, for inviting me to give this talk on learning to personalize in federated learning. And this work, I mean, I'm really excited to share this work with you guys, but this work wouldn't be possible without the contributions from the people in both Samsung and Cambridge. Yeah. Now I'm going to assume that everyone here is familiar with the fundamentals of federated learning, so I'm just going to skip all that. I'm going to skip the background and just hop right into the main motivation of our work. So the goal of personalized federated learning is to obtain a personalized model for each client which minimizes their local objective. And most existing personalized FR methods rely on fine-tuning on the client's dataset, right? So be it fine-tuning from a global model or a subset of a global model, or even further fine-tuning of an existing personalized model. Now, our goal here is to improve this fine-tuning process by learning a personalization strategy for each client. So the intuition behind this is that you have different data sets, you have different scenarios, different clients, and they all require different personalization strategies, right? So this strategy has a strong dependence on not only the client, but also the pre-trained model they use to fine-tune on the client, right? So for example, if the model is pre-trained on natural images, then we will expect fewer parameters to be updated when fine-tuned on natural images as compared to, say, fine-tuning on images in another domain like a product catalog page or something. So this is the framework that we propose. So during inference, assuming we have optimal personalization strategy, we take in the client's metadata, and this strategy would basically output personalized hyperparameters to fine-tune with the client's data to get the personalized model. Yeah. And I'll first talk about the different fine-tuning hyperparameters that we aim to optimize. So obviously there's a lot of different hyperparameters that you can optimize, like your number of epoch, the batch size, learning rate, weight decay, whatever. But we kind of narrow it down to two main ones, which showed promising results in previous works. So the first one is the batch normalization hyperparameters, right? Which explicitly deals with feature shift. So on the screen is just the standard batch norm equation. You have a pre-trained model that stores the estimated running mean and the estimated running variance, which is collected during the pre-training stage. We then want to learn to generate layer-wise beta, which indicates the degree in which the client should utilize its own batch norm statistics against the pre-trained model's batch norm statistics. Yeah. So in the extreme case, it would learn a beta value of, say, 0 for all batch norm layers. This means that the fine-tuning solely uses the pre-trained model's batch norm statistics. But on the other end, if beta equals to 1, then it solely uses its own local statistics, right? And in this case, it's really similar to one of the previous works, FedBN, which I'm sure a lot of you are familiar with. Basically, it's a work that keeps the batch norm layers local for each client, and these layers are not being sent for aggregation. The second hyperparameter that we optimize for is layer-wise learning rate eta, right? So in this case, there are also special cases depending on which layers get updated and which layers get frozen. But in the extreme case, if eta is 0 for the feature extraction layers and more than 0 for the classifier head, then it's similar to LG Fed average. But if you flip it around, then we have something similar to like a bunch of works that freezes the feature extractor and basically just train the head of the model. So how is this beta and eta estimated, and which metadata is used? So given the pre-trained model, we first get the batch norm running mean and variance, yeah? And then we do a forward pass on the client's data set on the pre-trained model to get the batch norm mean and variance of the input features, right? So there's a dependency on both the pre-trained model as well as the client's local statistics. We then measure the KL divergence of the distribution, and then we use it as input for our MetaNet. So in this case, our MetaNet is a personalization strategy, and it's essentially a really small MLP with one hidden layer. And it learns to map this difference in this distribution difference to get the beta for every batch norm layer. For theta, it's pretty similar. So we also do a forward pass on the client's data, and we get the mean and standard deviation of input features for all layers. Yeah. And we use this as an input to another meta net to get eta for each layer in the network. Now, in order to train these meta nets, it's quite straightforward. So our framework first takes in a pre-trained model. And then for each FL round, we want to generate hyperparameters for fine-tuning, right? So we take the client's metadata for each client, of course. And when we pass it through the personalized strategy, which is just the meta nets that learns beta and theta, and we use these hyperparameters for fine-tuning, yeah, using the client's data. This will allow us to obtain the personalized model in which we calculate the meta gradient to then update lambda. Lambda is the weights of the meta nets, right? So we're updating the meta nets to cater to that particular client. Yeah. And then this lambda would then be sent back to the server for Fed averaging. And this entire process is repeated for a few rounds till the meta net converge. Yeah. So this is essentially the whole approach of what we're trying to do here. So for experiments, we cover many different scenarios, right, to kind of validate how effective our framework is. So we use this bunch of data sets. CIFAR10, I'm pretty sure everyone knows, just a bunch of natural images. And you have CIFAR10C, which is adding different noise to these natural images. And then we have some domain adaptation data sets, so Office, Caltech, DomainNet. So these are basically data sets with marginal and conditional feature shift. And we also have the speech commands dataset, which each client represents a natural speaker. And our entire setup has different kinds of data heterogeneity. So we have the marginal label shift using LDA method, which is pretty much done in a lot of different works. We have an implicit marginal and conditional feature shift. And this is depending on the data sets, obviously the domain adaptation ones, as well as speech and the CIFAR10C ones. And we also have quantity scale where different clients have different number of samples, right? So there are a lot of different kinds of heterogeneity that we could select from. We also use a bunch of pre-trained models, which is either pre-trained using existing FL methods or using publicly available models. So you could start from a foundation model. Yeah. Our baselines consist of mainly fine-tuning methods. So because our Fed L2P mainly focus on improving the fine-tuning process, right? So we compare mostly on like fine-tuning methods. So we have fine-tuning just solely using client's batch-learned statistics. We're fine-tuning solely using the global models batch-learned statistics. And we also use the incoming feature batch statistics. So this is when the model uses some kind of instant normalization, which is quite popular in previous works as well. And we also have our method, L2P, without federated learning. So we are kind of learning meta nets on each client separately without any aggregation whatsoever. So it's similar to doing HPO or hyperparameter optimization on each client. Yeah. So there are tons of comparisons, including ablation studies for each data set, each pre-trained model with different types of data heterogeneity across all baselines, right? So each of these choices, they form a unique FL scenario where we evaluated our framework on. Right, so I'm just going to summarize the main findings of the paper. Yeah. So first and foremost, our framework improves performance in all these different scenarios that I talk about, right? So I give one example in the slide. In the table, we have data sets with varying marginal and conditional feature shift, along with some degree of marginal label shift partition using LDA. So the higher the alpha, the more IID the labels are, yeah? And you could see that our method compares with all the previous fine-tuning baselines, as well as our method without FL. And basically we beat everything. Yeah, that's it. The rest of the results are in the main paper. Yeah. One good thing about our framework is that it complements many of the existing FL methods. Because they only solely focus on the fine-tune process. So you could pretty much use it on any FL method that learns a global model or learns multiple global models. Yeah. And in this particular table, we show three different FL approaches. So fat average, perf average, fat value. You could use this to pre-train your model, and then given the pre-trained model, you could then plug our method to improve the personalized accuracy. Yeah. So I believe this is on the CIFAR 10 dataset. Yep. And the second last column is the most common way to fine-tune, right? It's like fine-tuning using the client's batch norm statistics. And the last column is our approach. In terms of cost and scalability, our framework is really cheap because we're only learning two really small meta nets, right? They only have one hidden layer. So the number of parameters is very small as compared to learning the entire pre-trained model. Yeah. Um, in our case, in our setups, the communication cost is just like 0.24 to 0.38% as compared to learning the pre-trained model. And during inference, it just takes 4.4, roughly 4.4% longer than regular fine-tuning. This 4.4% is mainly generating the hyperparameters from the client's metadata, right, in order to start the fine-tuning process. In terms of scalability, our method scales linearly with the number of layers, right? So it doesn't scale with the number of clients. So I think a lot of previous personalized FL works, they, like for example, using a hyper network to generate different client weights, they don't really scale well with the number of clients, and this methods usually fail when the number of clients go up to a really huge number. In this case, our method does not scale with the number of clients. You can add as many clients as you want. It does scale with the number of layers because we take the mean and standard deviation of the features for each layer as input to the metanet, right? So you could, like the more layers you have in your backbone model, the larger the metanet would be. Yep. But it scales linearly, so it's not that bad. Right. So this is kind of like a few interesting cases that we found of what our framework can do. There are many more cases in the paper itself, but on this particular slide, we present there's three of this interesting cases, right? So starting from the bottom left, this is the case where there is a feature shift. So the pre-trained model here is pre-trained on natural images, and we are trying to adapt it to a different image domain. Yep. And in this case, we observe that our method fedL2P learns to update all the parameters in the model. Yeah. And then at the top right, this is the case where there is no feature shift. So you're pre-training on natural images, you're fine-tuning on natural images, for example. Yeah. In this case, our framework learns beta equals to 0, which means that it basically uses the global model's batch norm statistics instead of the local one. Which makes sense, right? Because you're pre-training and fine-tuning on the same domain. Yeah. And then at the bottom right, this is a really specific case where there is no feature shift. Yeah. So same as the previous case, but the model is pre-trained on IID data. So the model is kind of high performing, it's pre-trained on like a centralized setting or in a federated setting with IID data. And in this particular case, because the model already performs so well, our framework just simply learns to stop the fine-tuning process. So eta will be 0 for all layers. In this case, you could save the computation entirely by not fine-tuning at all. Yeah. So as I said, you could find many more interesting cases in the paper. Another thing that I'd like to highlight is our approach learns hyperparameters that are well clustered according to the image domain. Yeah. So in this particular case, you have two plots here. On the left is beta, and on the right is eta. Yeah. And each row and column represents a different image domain in the domain net dataset. Yeah. So each block kind of represents the normalized L2 distance between all pairs of clients within that domain, and an off-diagonal block more than 0 indicates that the corresponding clusters are better aligned with the true domains, right? So I'll give you an example. Hyperparameters generated for clients with clip art images, right? So the first row, and hyperparameters generated for clients with real natural images. So the first row and the second last column, yeah, they have a normalized altitude distance of more than one for both beta and eta. What this means is that the hyperparameters used for fine-tuning clip-art images differ from those used to fine-tune natural images, right? So if you take the hyperparameters that's used to fine-tune between these two domains, you could actually cluster them. They're well clustered according to the image domain. Yep. Which is pretty cool, right? Because you could like the MetaNet learns to generate a different set of hyperparameters to adapt to different domains. Yeah. An exception to this is the case between the real natural images and paintings, right? So you could see, I think it's the third row and the fifth column, right? For both beta and eta, you can see that the box is kind of black because the number is close to zero. So this means that the hyperparameters used to adapt to paintings and real images are very similar, right? And this is mainly because of the inherent difficulty of how similar these two domains are. So if you look at like images, natural images, and you look at these paintings, they're actually very, very similar. Yeah. So that's the end of my talk. But if you barely listen to anything, this is the main key points that I want to highlight. So our framework FedF2P, we aim to improve this fine-tuning process, right? By generating different hyperparameters per dataset, per scenario, per client. Yeah. And these hyperparameters, they're generated through this meta nets, which are basically really small MLPs that use the client's local data statistics relative to the pre-trained model statistics. Yeah. And our model could be plugged into a lot of existing FL works, leading to a huge boost in performance. And it's also really scalable and efficient. Yeah. That's the end of my talk. Any questions?
Great talk. Very interesting method. If anyone in the meeting wants to ask a question, just raise your hand or signal and I'll let you speak. Or I'll also be scouting around on the Slack and other places where people post questions. Um, I I did think I saw Daniel N have his hand up during the talk. I'm not sure if that was just an accident. Um, but anyway, while people are thinking of questions they want to ask, I'll ask one and just say, where do you think we might see these meta nets being applied to next in the realm of federated learning? If you were going to use one right now to solve an applied problem, where would you want to sort of apply it?
Well, you could use it on anything really. I mean, right now we only show it on mainly classification tests. So
Hmm.
you could apply it on other tests. You could also like learn other kinds of meta nets. Actually, we just pick two of the most popular hyperparameters. But so for example, you could, I don't know, learn to stop or learn the number of epochs. I think that would be useful to
Hmm.
save computation because on-device training is quite expensive. So I don't know, maybe by looking at the client's distribution and taking the entropy of it or taking the number of data samples and fitting it through a MetaNet with the number of fine-tuning iterations, it's able to tell you when to stop the fine-tuning process. That would be useful. Yeah.
Hmm. I see. How generalizable do you think that sort of learning will be? Do you think people have to learn it for each combination of data, task, architecture, and so on? Would you think those sort of
It
meta
depends
nets?
on which hyperparameters are most important for the target task that they are learning. Yeah, in this case, I mean, in classification, you have a bunch of previous works that they are proposed to free certain layers or to keep certain batch num layers fixed or something. So it was pretty clear to us in this particular task that these are the hyperparameters that we need to focus on.
I see. I see.
Um, yeah, or maybe if you're working in if you're working with like generative models and stuff, maybe you could have like a set of pre-trained normalization parameters, and then you could learn meta nets to learn a linear combination of this normalization parameters, something like that. So it's really up to the scenario of and the task that you're targeting.
I see. Cool, cool. Let's see if there's any questions. Um, yeah, one question is, how well do you think this would work on audio tasks? I guess they're thinking about these cases where you want to personalize an audio model. Do you think it would work well in that case, or maybe you've even tried it already?
Yeah, so we tried it on speech commands, but we tried it on the simpler 12 class version of speech commands. Um, and we see that that leads to, I think, a 20% improvement in accuracy and performance. And we also tried it on like unseen clients during the pre-train stage. So clients that basically not seen during the pre-train of the model. And we also tried it on unseen clients during the training of the MetaNet. So these are clients that are unseen in both the pre-train stage and the MetaNet learning stage. And both cases lead to huge gains because essentially after you learn the MetaNet, you could just plug it to any new client that joins and just use it, right? Um, you don't have to relearn the MetaNet each time a new client joins.
I
But we
see.
haven't done it on more complicated speech tasks, I guess. Yeah.
I mean, another question here is just saying that since you presented this work back in December, I guess it was, in NeurIPS, they're asking if if anyone's contacted you about trying to use your work for their particular, basically bolt on like your method to their method to see what would happen. Have you had much
Yeah,
follow-up?
so I've received two emails from two separate people. I think one was interested in applying this to LLMs, to large language models. And then another email was interested in applying this to self-supervised learning.
Oh, cool.
Yeah.
Yeah, two pretty interesting areas.
Yep.
Well, I guess we're running a bit low on time. So thank you again, Royson,
Cool.
for
Thank you.
really
Yep.
awesome. Thank you so much.
Thank you.
And I can introduce our next speaker. And so our next speaker is Herbert. He is at the Technical University of Munich, and he's going to be talking to us about some collaborative work he's been recently diving into as a result of the EU AI Act starting to take shape. And in the process of working on this project, it actually went through a couple of revisions, and we sort of got to understand exactly what it was trying to go after a little bit more precisely, although it does look like it'll take quite some time before we fully understand how it's going to be kind of implemented and interpreted and so on, which is part of the exercise he was looking at. I leave it to you, Herbert. It's been wonderful looking at this topic actually with you.
Great, thanks, Nick. I think, yeah, perfect. So hope you can see my screen and hear me well.
Yeah, we can hear you. We can see your slides.
Perfect. Okay. Yeah. So, yeah, thanks for having me, Nick and Daniel. I'm really excited to be talking about our most recent work on federated learning priorities under the EU AI Act. This is joint work with Alex, Bill, Shiqiang, Nick, Ruben, and Arno. And you see there are quite a few institutions involved. So we really tried to take a broad look on this topic. So this talk is organized along four major points. So first of all, I'll briefly give an overview of the AI Act itself, how it's organized, and what we as researchers and also sort of technical practitioners can expect from it. Then secondly, I will go deeper into what does this new regulation mean for federated learning, at least in how it's available, or how the regulation is available at the moment. Then the third part will be about the three cornerstones that sort of concern federated learning and what sort of new research priorities we can derive from that. And lastly, a brief stint into
what other regulations are coming our way in different regions and countries. So with regard to the EU AI Act, it's organized based on a risk-based assessment. And with the latest revision that has become available end of January, there's now also a section on general purpose AI. So general purpose AI generally sort of contain everything that has to do with foundation models and models that use training above a total training load of 10 to the power of 26 floating point operations. But in this talk, I will mainly focus on the risk-based assessment as it was sort of initially introduced back in 2022, which has 4 categories. So the top level is unacceptable risk, meaning applications that are sort of illegal to provide. This, for instance, refers to biometric applications with some very strict exceptions for governments. Then the second sort of tranche in the pyramid is high-risk applications that pertain to medical devices and also things like job application pre-screening. So whenever you sort of apply for a job and something automatically selects applications, this also falls under the high-risk regime here. Then we also have limited applications, which are, for instance, chatbots like ChatGPT, and minimal risk applications that are highly specialized models, for instance, for decision support systems in corporates. So as federated learning is originally designed for private and very sensitive data applications, in this talk I will focus on the high-risk tranche here that asks us to develop extensive quality management techniques. Whether it's for federated learning or any other AI application doesn't matter here. But as said, federated learning is specifically made for those sort of very sensitive use cases. And the objective within the high-risk category is really to develop trustworthy AI applications. And in case of federated learning, we see 3 major assessment criteria here. So number 1 is data governance, number 2, energy efficiency, and robustness. And all 3 of them bring new challenges to the field of federated learning. So let me start with data governance. And this is probably mostly found in FL Ops applications right now, but the EU AI Act sets out very strict and extensive regulation in case of high-risk applications here. So the objective of data governance is to mitigate bias that originates from data and also prioritizes privacy in form of GDPR. So bias prevention, as it's stated in the EU AI Act, is really a matter of appropriate data pre-processing. What appropriate means is depending, obviously, on the task itself and fairness considerations. Both things are very challenging in federated learning to achieve since we are not able to really see input data and interact with the input data apart from feeding it into the local models at the clients. But what's noteworthy here is in terms of fairness, there has been quite some progress in federated learning with works like Q-FAIR federated averaging, for instance, that try to have or create very representative models across all clients. And the second big piece is GDPR. I mean, everybody who's read a federated learning paper may have stumbled across the word GDPR and privacy regulation. But what does this mean specifically for us? So GDPR sets out 3 points that we need to address when working with federated learning. So number 1 is security while processing data. This means we have to make sure that data is only used sort of in the way it's intended to be, and we really minimize risks of data leakage. The second part is the right to information. Which means that whenever we have a client provide data to us as service providers, they can always ask, has my data been used and how has my data been used? So for federated learning, this is at the moment a challenging question to answer. We either have to keep track of what clients have participated in training, or have some way of identifying what data has flown into our global model, which again is almost impossible to do. But nonetheless, this requirement will become very important for anybody doing federated learning. And the last point is consent-based data processing. So this means whenever we have a application, users give their specific consent to us processing their data. But once they revoke this consent, we immediately have to remove that data. And this calls for model unlearning, which is a very hot topic in machine learning in general. And there is first progress in federated learning as well by some people at IBM Research to really look into how can we unlearn models in a federated setting, such that we can, in case of GDPR, provide compliance here. Second big sort of element here is then energy efficiency that really calls for sustainable training and deployment methods. And in case of federated learning, what's really interesting here is we might see new benchmarks coming up because the EU AI Act or in the scope of the EU AI Act, the European Union has established an AI office. So basically the interface between sort of regulators, practitioners, and researchers. And they are calling for common baselines and KPIs that should define how we do machine learning or deep learning. And for federated learning, we have to come up with those baselines and meaningful KPIs that resemble those baselines. The second part within energy efficiency is we also have to account for the total energy incurred in a federated learning system. What this means, I'll come to in just a brief moment. And last one, and a very important point is that with the privacy methods we currently have available for federated learning, right? So, and I'm referring to technical privacy, they all come with a certain overhead. So what we will likely experience is a natural trade-off between privacy and energy efficiency. And the last sort of big building block is then robustness, which refers to consistent model performance. I mean, this has been a focus in federated learning for a very long time. But now we have to look into how do we ensure model quality, and this is interlinked with data governance as well, by using certain reference data sets. They are not created yet, so they have to be established, have to come from researchers and practitioners, but this will be a priority inside the AI. Then what's also important, and this will be very important for those technical privacy techniques that we have in federated learning, is model validation or inspection. So what we generally see is validating models on clients can be very challenging. Right, so we can have validation strategies run on clients, but in light of the EU AI Act with those reference data sets, this can become a challenging effort. So to sum it up, the EU AI Act will put a lot of, especially data governance regulation on us, but this will help us improve the quality of federated learning systems, I believe. And overall, if we don't comply with the AI Act, this can cost up to 35 million euros or 7% of gross global revenue, whatever is higher. So we see there's substantial financial sort of penalties if we don't comply. So, but let's now take a deeper look into each of those pillars and understand what this means for federated learning in detail. So in terms of data governance, whenever you read a federated learning paper, you usually find at least a sentence about GDPR compliance of federated learning. What we asked ourselves is this really true? Do we have full GDPR compliance with federated learning as it stands right now? And the question is really, really hard to answer because what we have to distinguish between is technical privacy, so in form of, for instance, differential privacy, secure multi-party computation, and homomorphic encryption, and regulatory privacy, which is this enforced by law itself. And what we find is that this is an an unsolved challenge or unsolved problem. And on top of that, we also see that a technique like differential privacy works very well in scaled systems and provides technical privacy or tight technical privacy guarantees, as can be seen in works by Andrew or McMahon. But for smaller systems, say we want to fine-tune a transformer model with for email classification, as you would, for instance, see it in job pre-screening applications, we see that achieving tight privacy guarantees comes at significant costs, right? So this is depicted here, and these substantial costs mean nothing else than increased energy consumption to achieve a certain training target. And also, as I said, that there is a gap between technical privacy, especially in the case of differential privacy, and regulatory privacy. For the cryptographic methods, SMPC and homomorphic encryption, they provide secure computation, and secure multi-party computation allows us to compute global models from encrypted client updates, but comes at significant communication costs. So we have a quadratic communication cost component, which means scaling is rather expensive. And also, if we remember from the requirements set out by the EU AI Act, this whole point of model validation and model inspection is very important to be legally compliant. So this is possible with SMPC and differential privacy alike, but for homomorphic encryption, the situation is currently a little different. Here, the server itself must never see the global model. And as such, the validation of a model is challenging to achieve right now. But again, if we emphasize research or put in research efforts, we can potentially find model validation strategies that work with homomorphic encryption as well. What's also very interesting is that when we sort of downscale a federated learning system with differential privacy, we exhibit those costs. And whenever we scale up a secure multi-party computation system, we exhibit additional communication costs. So we see a privacy and energy trade-off in each of these approaches, but also an open question: what is the right privacy or security technique to choose for a certain system? So this is it about data governance. Now let's look into energy efficiency. And for energy efficiency, I earlier said it's about total cost in a federated learning system. And what we've been looking at was a very conservative approach here that really takes into account every single piece that is involved in a federated learning setup. So what we can do is we can measure the compute power or the sort of the energy used for compute on the clients and the server directly. So as we can either request this as metadata or measure it in real time. But what's very challenging to measure is the cost of communication. Luckily for that, in 2015, Vishwanath et al. Introduced the per bit communication cost model that allows us to really trace how much energy a certain bit that we communicate consumes while traveling along the communication chain. What's, however, noteworthy here is that to effectively use the per bit communication cost model, we must know the energy characteristics of every hop we take, right? So we can, with, for instance, traceroute, the traceroute library, we can trace whatever hop we take, but we also need to know how much energy is consumed per bit. So this is still a limitation that's open, but could become relevant to solve in light of the EU AI. And lastly, we have robustness, which is very closely tied to energy efficiency. Why is that? So federated learning as such is a data parallel processing paradigm. And this means whenever we train on multiple clients in parallel, and then we validate our model before starting into the next training round, or we validate in a certain frequency. So what we've done here is in this experiment for fine-tuning a BERT transformer for email classification, we validate every 20 rounds with a total training time of 2,000 federated learning rounds. And what we see is to achieve a target accuracy of 50%, we take longer in terms of time, but also we consume significantly more energy. Why is that? So for compute, obviously, we're computing data parallel. So there's more computation involved than centralized on a single machine. But also we have this idle time here. And this idle time is basically time the system sort of sits idle while validation of the model is happening. And we are, as said, we are validating every 20 aggregation rounds. And in general, this can really pose a challenge when it comes to energy efficient federated learning. For this, we were thinking of techniques to perform validation in a certain frequency, right? So we really risk those idle times for potentially being providing a more robust model. Or we do, for instance, asynchronous validation at the risk of running into a less robust model and having to redo a few steps. So again, this is an open question, but this can become very relevant under the EU AI Act. And also what is noteworthy and special to the EU is the structure of energy cost. And this is why we really think energy is an important component in federated learning. So what we see is the generation and taxes of a single kilowatt hour of energy are declining. But in 2026, the European Union intends to introduce a market-made price for CO2 certificates. So, and experts now estimate that in the best case, we pay 65 euros per metric ton of CO2, and in the worst case, up to 300 euros. So this means whatever we save here in terms of the gross energy price, we can pay extra in terms of CO2 if we all emit a lot of CO2 by 2026. So overall, this underpins why energy is such an important component in federated learning. So now that I've outlined a lot of challenges that federated learning faces in the EU AI Act, let's look at some qualitative benefits that federated learning brings in by design. So federated learning, as we move models to the client, we get access to siloed data, right? So there's no need to move data from A to B. And this can really help us break open data silos and also account for this whole point of reducing data bias as we have a broader database basis to train our models on. The second point is simple data lineage. This is a requirement introduced by GDPR. So us as service providers, whether it's open source or commercial, we have to keep track of where is data used and where do we have potential data leakage risks. And in federated learning, input data can only be leaked at the client as we're not moving data. And this is obviously only given if we employ secure and private computation techniques in an appropriate manner that is, as said earlier, yet to be defined. And lastly, low bias models. Why low bias models? So federated learning can enable continuous learning. And this means we can adapt on the fly to our client bases and really learn what clients or what data clients have available for us. And with that, the system automatically adjusts to the needs of clients that will eventually use the model for inference purposes. So now that we know about the challenges in depth and qualitative benefits, we think there are especially 4 points that need to be addressed for federated learning to become AI compliant. So first and foremost, we have to close the gap between regulatory and technical privacy. Then we also have to look into CO2-based regularization of federated learning methods. So similar to as what we've done with using the number of samples processed on a client to create a weighted average, we could also look into how we can use CO2 as a regularization criterion to establish green federated learning systems. Third point is establishing technical frameworks that enable AI compliance. So if we want to drive the adoption of federated learning on a broad basis, we have to make sure that people who really apply federated learning get a tool set which they can use to determine the appropriate measures for AI compliance. And last but not least, the comprehensive baselines for federated learning. This entails both technical, like full federated learning pipelines that measure relevant KPIs that are also yet to be determined, and also reference data sets that we can use to evaluate the quality of models produced in federated learning systems. So this closes the part between the EU AI Act and federated learning. Now let's take a final look on what else is coming our way. So there's other countries that prepare AI regulation similar to what the EU has done. So in the US, there's the White House Executive Order on AI that was released in October 2023. And they are establishing guardrails for AI applications based on the total compute used in training. So for instance, for general purpose AI, they also set out a threshold of 10 to the power of 26 floating point operations to, as sort of a categorization for machine learning models. And what is also very interesting is this executive order contains a call for a research agenda to explore the regulatory compliance of differential privacy, to really evaluate how can we close the gap, or can we even close the gap. And in Canada, we see Bill C-27. They set out their priority to align with international AI laws, so whatever is established in the EU and in the US. And they also mentioned the EU AI Act as a lighthouse regulatory framework, which they see as a convergence target for themselves. So we see there's a lot of movement going on right now. And we definitely have to act in order to really keep the practicality of federated learning going forward. So with that, I conclude my talk, and I once more thank the amazing people I got to work with on this piece. Yeah, that's it. Thank you.
Thank you so much. I think it's really interesting and really kind of timely period for federated learning. So we can start to see how some of the benefits that have been around since its inception, I think, are really going to start to crystallize as we see people understand how they should regulate AI more seriously. And I think what this work is showing us is that many of the pieces are already in place, although there are certainly quite a few bridges to be crossed. But that is true actually of all the other learning approaches too. I'm sure they have other bridges I need to cross to be compliant. Let's see if there's any questions from folks. I'll scout around on the Slack. And if anyone here live in the room wants to ask a question, just raise your hand. Could be a comment as well, of course, not just a question. While I look around.
Maybe a super quick question from my side. First of all, thanks. A super interesting talk and great summary of what is happening and how it relates to AI and federated learning. I'm wondering, apart from regulations in the US and in Canada, are you aware of other similar regulations around the globe that are being thought about maybe or already proposed?
So I'm not aware of any other specifically, but if it develops a similar dynamic to GDPR, I wouldn't be surprised that something's coming up within the next couple of months in other regions as well.
So, Daniel, did you have any other follow-up questions to that, or?
No, thanks.
Okay, just checking. We have a question here. They're asking, where do you think? Well, I guess they're trying to say, given this situation with the Act and how federated learning needs to evolve to meet some of these needs, once it makes those bridges, where do you think it'll be applied to? Kind of what sort of opportunities arise in different application spaces, do you think?
Yeah, so as I said initially, going back to this slide, I think federated learning is meant for high-risk application, right? So anything that involves sensitive data and that really requires to be rigid on quality. Yeah, so this involves medical devices. So I'm currently working with an industry partner on medical imaging. And they are exploring this for multiple of their MRI machines. So they have different generations. Yeah, so this is where I currently see this federated learning going.
Another question here is about energy and there seems to be many, I guess, from what you said here, there's a lot of unanswered questions about how we exactly should measure energy and compare it to other approaches. So the question was, what do you think is the fair way to measure energy used by different, quite substantially different ways of doing learning? Centralized, you might have completely just entirely locally, there's federated and so forth. What do you believe is the right way to account for the different factors that get consumed during those processes?
Yeah, so that's a very good question. Thanks to the person bringing that up. As I said during the talk, I think for those comprehensive baselines, taking a conservative approach is the best way to go. That's my personal opinion. But again, what we have here is a challenging situation of network providers making the data available, like in terms of whatever power we consume per bit, for a federated learning service provider, for instance, to calculate those costs, right? So I think this will be a trade-off between really being thorough and taking into account every single bit of energy consumed and practicality.
Yeah, makes sense. Yes. It's quite interesting to see that the Act really calls out a number of things that need to be measured in some way, and yet we haven't really agreed upon how to measure those things yet. So I guess it's really pointing it's pointing some interesting gaps that are certainly going to have to be filled, given what's been called out.
Yes, I think to add to that, what's very relevant to know is that the EU has established this AI office, and they are really seeking collaboration with practitioners and researchers to develop such guidelines, right? So to really find a balance between every nitty-gritty detail, if you will, and the practicality of those approaches. Yeah, so I think there will be a lot of discussion also publicly going on over the next couple of months.
Great. Well, I didn't see any other questions out there, and also we're running a bit low on time. So again, thank you so much for sharing this piece of work with us. And I understand, is it on this on archive yet? This position paper?
We're waiting for the link. So it got put on hold. Whatever filter we ran into, I don't know. But I'm sure we can make it available on YouTube, in the YouTube comments box once it's available.
Excellent stuff. Again, well, thank you very much for sharing. That means we've reached the end of this Flower Monthly for February. Thank you to Herbert. Thank you to Royson. Thank you also to Daniel for that exciting summary about 1.7 release. It's all happening here. And join us again in March. It'll begin the first Wednesday of the month, which will be March the 6th. We'll have some more invited speakers. We'll have some interesting new advancements throughout the month, I'm sure, with Flower. And no doubt we'll have some new announcements related to the Flower AI Summit that would actually be taking place shortly after that Flower Monthly edition. So join us then. Thank you very much for joining us today, and take care, everyone. See you later.
Thanks, everyone.
Bye-bye.
Bye.